Hi guys, welcome to today's video, which is going to be all about ionic bonds. And so what we're going to be looking at is just very quickly what is an ionic bond, and I'll show you a couple of examples. So the definition for an ionic bond is over here. It's a bond between a metal and a non-metal atom by the exchange of valence electrons. So that's really important to understand that unlike a covalent bond, which is a video on if you want to have a look, where they share or overlap valence electron shells to get a full outer shell, in this case here, we actually exchange them. So the metal atoms give up electrons to the non-metal atoms. So there's a full donation of an electron in there. So I'm going to just start with a very simple example for you, and to understand this you need to have a bit of an understanding about like what we call maybe Lewis dot structures or electron dot structures. So an electron dot structure is where you draw an atom. So in this case I'm going to choose sodium here. Okay, so you draw the symbol for the element and then you put in the number of valence electrons they have. Now because sodium is in group 1, okay, it has one valence electron. Okay, so knowing the group of the periodic table is really important. So what we do for that is we just put a single dot here, okay, for sodium. All right, so it's a sodium with one electron, and that's how it exists in what's called an electron dot structure. If we bring that in together with chlorine, for example, all right, chlorine is in group 7, so VII, okay, which means it has 7 valence electrons. Now, if these two atoms are going to join, got 7 electrons here. When we're doing dots for them, we put them at 90-degree angles for each other firstly, and then you start pairing up. So here's our chlorine with 7 valence electrons. Okay, here's our sodium with 1 valence electron. Now, if they're going to bond, both of them want to get what's called a full outer shell. All right, now if you look at the electron configuration for sodium, and there's another video on that, the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. Okay, and the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Sorry, I just had to remember if it was in period 2 or period 3. So there's our electron configurations. What both of these atoms wants to do is get a full outer shell. Now a full outer shell is basically 8 electrons in the outer shell. So our sodium here, if this wanted to get a full outer shell, it could add 7 electrons, all right, to go 3s2, 3p6 and get 8 electrons in the outer shell. But it's much easier for this to actually lose 1 electron, because if it loses that electron, what will happen is that it will actually come down to this shell here and be 1s2, 2p6. So this 1 electron it wants to get rid of. Over here, the chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Now what it can do to get 8 electrons in the outer shell is just gain 1. Okay? It could try and lose all 7 of them, but it's much easier to gain the 1 electron. And when we've got metals that want to donate electrons and we've got non-metals that want to gain electrons, it makes a lot of sense that we actually do that. So what's going to happen is that this lone electron on the sodium here is actually going to leave that valence electron shell, and it's going to come over here to the chlorine. Now what that does to the sodium is it turns it into a positive, an Na+, because it's lost an electron. And because it's lost an electron, this 3s1 electron there disappears. And it now comes up with the electron configuration 1s2, 2s2, 2p6, which is a full outer shell. All right, 8 electrons means a full shell, which means it's happy. Okay, the chlorine over here, what now happens is that it's now got 1, 2, 3, 4, 5, 6, 7, 8 in there. So that 3p5 shell actually becomes 3p6. That is also 8 electrons, which means it is also a full shell. But because that chlorine has now gained an electron, that now has a negative charge. So what we've actually done is form a bond between the sodium and the chlorine, okay? And that bond that we have formed is our ionic bond, okay? So this is our ionic bond right here, where we have exchanged a valence electron between the sodium and the chlorine to get a full outer shell. Okay, So that's the idea of an ionic bond. I'm just going to keep this one short. Hopefully you can understand that all we're doing is exchanging valence electrons. The metals give up electrons in order to get a full outer shell. The non-metals gain electrons in order to get a full outer shell. And when we get that exchange of the valence electron, we form an ionic bond between them. Now, ionic substances exist as what's called three-dimensional lattices, okay? So they're not like molecules where you have like just one water H2O on its own. They actually exist as a three-dimensional molecule. So I'm just going to, three-dimensional lattice. So I'm just going to show that to you now. So as I was saying, when you have something like water, which is made up of covalent bonds, and there's a video on that, okay? A water molecule in solution exists independently by itself. So then there's another water molecule over here, and another one over here, and here, and here, and they're all connected by what are called secondary bonds. However, substances that are made up of ionic bonds, so salts is the classic example, they don't exist independently like that. What actually happens, and I'll go back to sodium chloride, is that you actually end up with something like this. So there's a sodium to a chlorine, there's the ionic bond in the middle, but we actually end up with a structure that starts to look like this, okay? Now, I'm only working on a board here, so it's really hard for me to show you 3 dimensions, but what actually happens is that we start to get this big molecule, I shouldn't say molecule, sorry, this big substance which goes in 3 dimensions. So not only are these bonds going in the X and the Y axis, they're actually going in the Z, so they come out of the board as well, so it's 3-dimensional. And this is what's called a lattice, okay? So, ionic substances exist as a lattice. What that means is that they're big 3-dimensional networks or structures. Now that has a couple of impacts upon their properties. Because there are so many bonds here within them, you have to supply a lot of energy to a substance like sodium chloride to break those bonds and turn it into a liquid. So if you're going to melt sodium chloride, turn it into what's called the molten state, you have to break this bond and this bond and this bond and this bond and all of them all the way throughout the 3-dimensional lattice structure. That requires a lot of energy. What that means is that they have very high melting points, okay? When you do break them, however, something really interesting happens. When you break these bonds, okay, you got to remember that what actually happened was that we formed that bond via the exchange of a valence electron. So that doesn't change. We don't go, not like the valence electron goes back. So what actually happens is that when you do melt it, you then end up with your sodium ions and your chlorine ions in there, okay? Now that's really important because when those ionic bonds are broken, whether by heating or by dissolving it in a liquid, you now end up with ions. And ions allow you to conduct electricity. So in the solid state, like we've got here, all the electrons, everything like that are in bonds. So solid substances like salt, all right, any ionic substance doesn't conduct electricity in the solid state. But as soon as you melt it, you form ions, which allow it to conduct electricity. When you dissolve it in water, you're also forming ions, which also allow it to conduct electricity. So it's quite interesting the effect this 3-dimensional lattice structure has on the properties of ionic substances. Okay? It means that they have very high melting points and they don't conduct electricity in the solid state. But when you melt them or dissolve them, they do conduct electricity, okay? Which is quite interesting. So, what I've gone over today is the definition of an ionic bond. It's where a metal and a non-metal atom bond via the exchange of valence electrons. And that's because the metals want to lose electrons, non-metals want to gain electrons. When they do that, they both get a full outer shell and you form this strong ionic bond. But when they exist together as a 3-dimensional structure, it makes them quite strong and hard. Alright, hopefully you've been able to follow this and it's been pretty straightforward for you. As always, if you've got any questions, just ask. Thanks guys.